Now going to look at the energy that we find in bonds. This particular video is going to cover the energy involved in ionic bonding, or the lattice energy. So we recently discussed ionic and covalent bonds. Of course, ionic bonds have a transfer of electrons from one atom to another, while covalent bond shares those electrons between the two atoms. So when it comes to energy, you can always think of this as if two atoms are coming together to make a bond, there must be a net decrease in energy, according to thermodynamics. Right? If you take two things and you come them together, that's not going to be entropically favorable. So we must have a negative delta H for this type of reaction to occur, and then have a corresponding negative delta G. So our bonded state must be lower in energy than the unbound state, or else we wouldn't see bonding occur at all. So let's look at a very simple case of sodium. Typically sodium is a solid at room temperature, and chlorine is a gas at room temperature. If we add these two things together, we get sodium chloride, or table salt, which is a solid. So everybody's pretty familiar with this solid. So if we think about all the things that have to happen for this to occur, sodium has to lose an electron, and then chlorine has to gain the electron. But before chlorine can gain the electron, it does have to break apart from Cl2 into two individual chlorine atoms. So if we look at our last chapter, we looked at ionization energy. So the first ionization energy for sodium was 495 kilojoules per mole, and that will be a positive value. So now if we look at the electron affinity for chlorine, chlorine releases 349 kilojoules per mole when that gains the electron, and that of course will happen twice if you balance our chemical equation. Now we have to also look at the energy it takes to break a chlorine molecule into chlorine atoms. And this is what's known as bond enthalpy. As you can imagine, it takes energy to break a bond apart. We're going to explore this topic in a whole nother video in a few days, but for now just realize it does take energy to break bonds. So to break a chlorine bond into two chlorine atoms, that takes around 122 kilojoules per mole. So if we add all these up, we are at 268 kilojoules per mole, which is a positive value. So something's not right here, right? We just said that we have to have a negative delta H for this reaction to occur. And indeed, if we do this reaction, we do see a lot of heat and flames given off. So we know that this reaction is exothermic. But according to our numbers, it says it's endothermic. So how can this be? Like, what exactly are we missing? So if you do recall, the ionization is the amount of energy needed to remove an electron from a gaseous ion, and we are just looking, we mentioned we started with the solid sodium, so we do actually have to turn that solid sodium into a gas, but of course this also takes energy, so that would make it even more, delta H even a more positive value. But the one thing we're not really accounting for is that there's energy released when two ions combine to form a solid. So this missing piece of the puzzle is called the lattice energy. That's the energy required to form an ionic solid from completely separate gaseous ions. And this must be a very exothermic reaction, or else we wouldn't see this reaction happen at all. So we can measure that energy using Coulomb's law. I mentioned in the last video that ionic bonding was largely governed by Coulomb's law, and here we have it in itself. So the energy that's released is equal to K, or constant K, or Coulomb's constant, times the charge of both species involved. Here we have a positive proton, a negative electron, so it'd basically be positive and negative 1 here. And D is the distance between those two particles. So you'll notice if you have a positive and negative particle coming together, you're guaranteed to get a negative energy according to Coulomb's law. And that is indeed what we see. So we did just cover a lot of different pieces. However, we can easily explain this using Hess's law. So if we look at an overall energy diagram, you'll notice that the second from the bottom blue line, we have our solid sodium, and we have our chlorine gas. We just have 1/2 of chlorine gas molecule. So if we follow that first green arrow up, the solid sodium is turning into sodium gas. So we're basically subliming the sodium. Then if you follow the second green arrow up, we're looking at the bond breakage of Cl2, or the bond enthalpy in Cl2. Then the big green line going upwards, that's the first ionization energy of sodium. So now we have a gaseous sodium ion. Then that first green arrow down, that's our electron affinity of chlorine. So the chlorine picks up that electron that sodium just lost. And you can see at this point we're still I have a very large positive delta H. Now if we look at the big green arrow going down on the right, that is the release of the lattice energy that comes from the formation of sodium chloride. So you can see that's very, very largely exothermic, and that overshadows almost all of those positive entropy steps that we looked at before, or enthalpy steps we looked at before. So we have an overall net delta H, which is negative, which is represented by that blue line. So that's the energy that we see, or that's released when we take solid sodium and chlorine gas and combine those together to get sodium chloride. So if we look at the lattice energy for a variety of different compounds, you'll start to see a number of trends. So first, if we look at all of the chlorides, we have lithium chloride, sodium chloride, potassium chloride, and cesium chloride. Those are all of the alkali chlorides. You'll notice that those do decrease in lattice energy as we go down the table. Then if we also compare, say, sodium fluoride, sodium chloride, sodium bromide, and sodium iodide, we also see a decrease as we go down the table. So in general, there is a decrease in lattice energy as we move down the table. You'll also, if you recall, the ionization energy is typically much lower at higher temperatures. So really, we need less energy overall to be released to form these compounds. If we move over to the second column, we start to see ions at multiple charges. If you think of magnesium and strontium, those are both +2 ions. So those have to undergo 2 different ionization energy steps. So in order for these reactions to form, we must have a large lattice energy to take into account those 2 ionization energies. Then even a little further still, we have magnesium oxide, calcium oxide, and strontium oxide. Those are +2 and -2 ions. So just like before, we do have a lot of energy that we have to overcome. And if you look at scandium nitride, that of course is a +3 and a -3 ion, so you can expect that to be much larger as well. All right, so we just saw a few cases where the lattice energy released when we form these ionic compounds is exothermic, and the overall process ends up being exothermic. But what happens when the lattice energy that's released is not high enough to shift the overall reaction to have a negative delta H? So would bonding still occur in these cases? So we can look at hydrogen. That's a very simple example of that. If hydrogen, or H2, would form via ionic bonding, hydrogen has a very high ionization energy, 1312 kilojoules per mole, and the electron affinity is pretty small. So we would have to have an extremely large lattice energy in order for ionic bonding to occur. So the better option for hydrogen is, instead of transferring that electron from one to the other, is to just share it in between. So what we see is that when the lattice energy isn't large enough to make the overall reaction exothermic, generally we see covalent bonding. And so what we see is that there's these electrons in each atom. They end up being attracted to the 2 nuclei of each atom. And we looked at that picture in the last video that had the 3 types of forces in covalent bonding. So we have those electrons that are being attracted by the protons of both different atoms. So if you were to take two hydrogen atoms and have those infinitely far apart, they wouldn't be interacting with each other at all. So you can sort of picture that at the very, very far right of this graph. And this is a potential energy curve for hydrogen. So as we start to push those hydrogen atoms closer and closer together, we start to feel that attractive force. The protons of one hydrogen start attracting the electrons of the other hydrogen, and vice versa. So that attraction force starts to pull each other together. And just like Coulomb's law, if you have a positive and negative charge interacting with each other, you do have a negative energy. So you can see that the potential energy starts to drop, slowly drop. As they come closer and closer together, eventually we reach a point where they do end up bonding and sharing those electrons between them. And when they reach their optimal distance, to the lowest point in energy, that's when we have the bond length, or the distance between the two hydrogen atoms. So if you start to push those two hydrogen atoms closer together, that's when you start having these two positive proton cores. When they start getting closer together, that's when we start feeling much higher nuclear repulsion. So those protons and the hydrogens are pushing each other away. So if you tried to smash those two hydrogens together, we start seeing that large potential energy increase as we go to a shorter bond distance than what's optimal. And that's why that energy shoots up quite a bit. So it's like trying to put two positive sides of a magnet together. If anybody has tried to do that, you realize it's basically impossible, and it would take a lot of energy to overcome that. So one thing you'll note about this graph is we have a point labeled bond association energy. So that is the point where we looked at the chlorine molecule earlier. That's the point when you have two molecules or atoms bond together that are sharing electrons, and once you apply that much energy, they're no longer sharing those electrons. So you can think of, as this graph goes out to bond length infinity, that's essentially going to be the energy required to do that. So earlier, I think it was 122 kilojoules per mole. So here the negative potential energy, if this was a chlorine atom, it'd be negative 122 kilojoules per mole. So to sum everything up, lattice energy is exothermic, and that must overshadow the ionization energy and bond enthalpy in order for the ionic bond formation to occur. That's one of the key ideas here. So you should be able to recognize the sign of delta H for each individual step. Also, another key idea of this video is that covalent bonds have a minimum potential energy, and that's when those atoms have the lowest possible energy that minimizes proton-proton repulsion, it minimizes electron-electron repulsion, and it maximizes that proton-electron electrostatic interaction. So that's the point when we have the lowest negative value. That's it for this video. Next, we're going to look at bond enthalpy and bond association in much greater detail, but not until after we start looking at Lewis structures and structures of atoms. Then we'll pick up and do a much more advanced treatment of that at that time.